At this series parallel circuit, here we have the conventional charge leaving the positive terminal, coming around through here, and all of the electricity is going to go through this bulb right here, and then it comes over here, and then there's a fork in the road. Some of the electricity is going to go this way, some of the electricity is going to go that way. And then the two currents are reunited, and then it all goes back to the negative like that. If I was going to draw this in a more textbook rendition, it would look something like this. You still need to see that? All right, as you're copying that, I'll see if I can demonstrate this. Dan, you want to give me a hand? Y'all.
What would like a circuit breaker do?
Breaks the circuit.
Good question. I'll answer that as soon as I get done with this demonstration.
Wasn't that a hard question? Yeah, that's fine.
Okay. So hold like this. Make sure you're not touching any metal. Okay, but you gotta hold it like that so they can see. Okay, a little bit higher if you don't mind.
No, that's this is big.
So step a little bit over. So basically, do you think all three bulbs are going to be equal brightness?
Yeah, sure.
No, it's serious.
No, the middle one will be dimmer. Dan, can you move the
Good question.
What do you think, Julie? What do you think is going to happen?
Oh.
You can freeze your hand.
The last two on the right, these two over here, think are going to be dimmer. So you think this one over here is going to be brighter. Let's take a look.
I think the opposite.
Okay.
Good call. Good call.
Good call, Joey.
Nice.
Wow.
Nice.
How'd you know that?
Clutch.
I was just kidding. You know.
Julie, if you could come up here and do me a favor. Dan, come reach over the table again. I'm going to do the same thing. Just don't touch any metal. This time, I'm going to ask Julie to unscrew the bulb on the right, all the way to the right, but hold it up so everyone can see. We're going to do this live here. Whoa. We're going to do this live. Okay, don't touch any metal, just the glass. Now, when she unscrews that bulb all the way to the right, what do you think is going to happen?
Lefty
We
looking
can't
brighter.
see. Julie, don't.
What happened to the middle bulb?
It's not the same brightness as the other bulb.
Yeah, it went a little brighter now. Basically, what kind of circuit do we have now?
No, seriously.
Parallel.
No, parallel.
Yep. Parallel. You have a parallel circuit.
Parallel.
Well, let's take a look at the board here. Step over, Dan.
Well, no, it became a series from a parallel.
Are you serious?
Right here, if we undo this bulb right here, that's what she did. She unscrewed it.
That's a series.
Okay,
It's just a series.
that's a series circuit.
Ooh, in
Okay,
your face.
look. The positive charge goes through one bulb, and it goes through the other bulb, and goes on home. That's a series circuit. Okay, I'm serious.
That's when they're both the same brightness, series.
Well, series and parallel, they both could be the same brightness. It's this time they're sharing the voltage, they're both dimmer. Okay? Okay, now let's do the same thing, Julie, but this time I'm going to have her unscrew this bulb over here. This time what's going to happen? Bring it up, Dan.
That's a parallel. They're just gonna go.
Hold on, up higher, up higher.
Should I
Wait.
screw that one in?
Yeah, screw that one in first. Let's get them all going. Why don't you come from behind so they can see what happens? All right, so basically, let's get them all going. Come around. No, come between the two of us, Julie. Don't touch any metal. As soon as she unscrews that one, what happened, everyone?
Circuit dead.
The circuit.
Everything went out, yes?
Yes.
That makes sense?
Yes.
Thank you,
Eight
guys.
circuits.
If we unscrew this one here, basically we have an open circuit. See what I'm saying?
Short circuit.
No, not a short circuit.
Open. So.
Open circuit, because it's like in a drawbridge that's up. You know, it's open. No way to get across. So basically everything goes out.
What was a short circuit?
A short circuit would be like this. If I came in with my wire and I just connected the positive straight to the negative. So it's like a little shortcut, and there wouldn't be any resistance in between. So massive amount of charge flowing from the positive to the negative. So massive that it's dangerous, you know. A lot of heat generated.
Like, so how's that happen?
Oh, I got a question.
If I touch the two ends together, You're like, whoof! Scary.
Can we try?
Mr. Ash.
Oh, I hate doing this, people.
Mr. Ash.
It's really scary.
So you're doing it?
Do not try this at home.
I gotta ask you some
Oh my.
or
No way you're doing this.
asking you
No way this is-
question.
I'm gonna have Trinos we can
Oh!
Oh my god.
I hate doing that.
Oh my god.
Short circuit.
I like that.
So scary.
Massive amount of current.
Yes, that's right.
There you huh?
Just like screams so
I'm
loud.
up.
Wait, I have a question.
I didn't get shocked. I was touching the rubber insulator.
But there's a chance you could have died.
No.
What do you mean?
No, the wires were, if there was any chance at all that I would feel the slightest bit of pain, I would have done it. Okay? Alright. Now there's a good question about a fuse.
Can we do it again?
Oh,
That was so scary.
Yo,
It's quite scary.
It was like cool though. Like,
It's quite frightening.
it was cool. It was very cool. Mr. S, that was so cool.
I was
Well,
petrified.
get it?
Are you serious?
Cool. No, I'm
Okay,
I'm-
really, the
I'm
corny
negative.
jokes in here have got to stop.
Thank you, Hannah.
Like,
Thank you.
really.
Thank
Why?
you very much. You finally said that.
If they don't stop, I'm gonna have to give you more homework.
Okay, that was.
Okay. Now,
That's funny.
let's look at these two simple circuits, yes? Each of them have one single light bulb. Right now they're equivalent. They might have a little bit of a different look, but that's the same circuit. One the bulb's on the left, one bulb's on the right, yes? Now, the one on the right, if I add in more resistances in series, I'm serious, people. Every time I add another one in resistance in series, what happens to the total resistance of the circuit?
Increases.
Well, this is a series circuit,
Nothing.
okay?
Kidding, no, it
It decreased by like 1 over.
No, that's
No, it increases. It increases.
Series circuit, every time you add another resistance,
It does increase.
the total resistance goes up. Yes?
Because it's harder to get through. It's like
It's harder to get
speed bump,
through.
Speed bump. Speed bump.
It's like 2 speed bumps.
Speed bump.
Yes?
Yeah.
And then if we look at the total, current, if the voltage stayed the same and the total resistance went up, what's going to happen to the total current of that circuit?
Go down.
It's going to decrease. It's going to go down. And if I add another resistance in series, what would happen to the total resistance? It would go up even more. And if the resistance of that circuit went up even more, same battery, what's going to happen to the total current? It's going to go down. So every time you add another one in resistance in series, the current just keeps getting smaller and smaller. However, in parallel, if I add another resistance in parallel, what just happened to the total resistance?
Remains.
It's like by 1 over.
Now when that charge comes around the corner, gets to this point, it's like a 2-lane highway now. There's 2 ways to get through. It could go this way, or it could go this way. So now that there's a 2-lane highway to get through, what happens to the overall resistance?
Decreases.
It decreases, and you would see that with that formula if you crunched it out. The total resistance decreases, yes? And then basically, if we look at the totals, if the total resistance decreases and the voltage source remains constant, what's going to happen to the amount of current coming out of that battery? It's going to increase. That battery is going to be shipping out more current. And if we added another branch in parallel, yes? What would happen to the total resistance now?
Even less.
It's even less. It's like a 3-lane highway. There's 3 ways for the charge to get through. So basically, the total resistance is even smaller. So what's happening to the total current coming out of the battery? way bigger. Yes.
Wait, can there ever be like, you know how you keep adding on another one? Like, can you ever have two resistances like in one?
Stretch one branch.
Yeah.
That's two. Yes.
What?
And if you did,
Oh, but
then it would be a little bit parallel and a little bit series. And you know what you'd be dealing with? A combination circuit, and that's what we're going to be dealing with today. Good question. So, do you guys see how every single time you add another resistance in parallel, the total resistance goes down? You just add it another way to get through. So the total current goes up. It's getting a little dangerous, people, because the amount of current going through this wire down here is getting bigger and bigger and bigger. And when you have more current going through a wire, that's like more collisions. And you saw what happened to that pickle. You saw what happened to that hot dog. It generates heat.
And then we cause the fire.
Things could start on fire, people. So there's a safety mechanism. It's called a fuse or
A circuit.
a circuit breaker. A fuse is easier to understand. So let's look at a fuse, and then you just need to realize a circuit breaker accomplishes the same thing, but instead of having to completely replace it, you just have to flick it back. So here's the deal. Right in this section right here, we're going to put a special wire, and we're going to enclose that wire in a fireproof case. And basically, that little blue wire on the inside, it's not really going to be blue, I just drew it blue to distinguish it's a little bit different kind of wire, has a high tendency to burn out, to just completely start on fire if too much electricity is going through. Because it could get dangerous if you had so much current coming out of the battery here. You know, you could start a house fire. So what we do is we put this fuse, this safety device, and if anything's going to start on fire, guess what's going to start on fire first? The fuse right in here. And if it does start on fire, we're safe. Because what is that little piece of metal enclosed in? A little fireproof box. So that will blow out first. And if it does blow out,
Oh, so that's why when people are like using their hair dryers all at once.
yes, if it does blow out,
Oh.
what happens to all the things?
Shut up.
They shut off. It's an open circuit, you know? And like in olden times, everyone had fuses in a fuse box, and if they had too many things on, they would blow a fuse, so then you'd have to go down into the basement and open up the fuse box, and it looked kind of like a battery, but a little bit different look, and you'd have to pop out the fuse and put a new fuse in. Today, we don't have fuse boxes. We have circuit breaker boxes, and they work the same way, but they're not like disposable. They're completely reusable, and if too much electricity is going through, it pops the circuit breaker open, and then you have to go and re-flick the switch up. So that's what a fuse and a circuit breaker does. It's a safety device. Yes?
So then, like, how does like a fire like start from electricity? How can like at one time I like read an article about how like electricity like started a fire and like burned down a whole house.
Well, if it's an older home, okay, you could just have like faulty wire that's no longer covered with you know, like an insulation coating, okay, and basically you know, even though you have your fuse protector there, you know, if the wire gets like old and loses its covering, you know, maybe it's like up next to a piece of wood and the wire's heating up just a little bit, you know, it could start a fire. My dad rented a farm, not his own farm, but he rented a neighbor's farm, and it had a very, very old barn that really wasn't being used seriously, and we used to put some of our hay in that barn, and we had some young animals in the bottom of the barn, and we had this hired hand, Charlie, and Charlie was an interesting character, and he didn't like going up in the haymow in the dark to throw down hay, you know. So he reconnected, turned on the electricity to this old barn, so that the lights up there would go on, so he could see what he's doing. Well, he should have never done that because it was like faulty wiring, and eventually, I think during a storm, when things got wet, the electricity somehow or another started to like, instead of just going through the wires properly, it was somehow jumping onto the wet wood, and it was like creating a little arc, and to make a long story short, that whole barn burned down.
You put the animals?
There were some pigs in the bottom that couldn't get out.
Oh.
It was very upsetting, because
I hate
At least you had that with bacon.
yeah, no, there was nothing left.
Must
So
That's really what-
anyway,
really-
back to today's lesson. How are combination series and parallel circuits solved? So that same circuit, okay, that same circuit could be redrawn like this.
You fire Charlie.
No, it was a.
An honest.
You guys eat the pigs up.
Yeah, there's nothing left.
No, there was nothing too much left.
Smoke it.
Here comes all the electricity. It all goes through here, and then it splits. Some goes this way, some goes this way. That's why this light bulb was brighter. It was getting all of the current. All of the electricity had to go through it, but then when the electricity got here, it splits. Some went this way, some went that way. So these were like smaller currents compared to the whole current. So these were lit up a little bit less bright. So what we're going to do is work out a sample problem, and we can make this a 12-volt battery. And why don't we make this why don't we make this 2 ohms, and we'll make this 4 ohms, and we can make this one up here 8 ohms. And our mission is to solve for the current in each resistance and the voltage across each resistance. And notice the wording, that it's a different terminology. You know, find current in each resistance find voltage across each resistance. The current goes through the device, but voltage is like a measurement of the energy before and after. So you say the voltage across each resistance. And the method used to solve this, folks, I personally call like a boomerang method. You know how with a boomerang, you throw the boomerang and it goes, you know, and it comes right back to you? Yes? Well, basically what we're going to do with this problem is we're going to start off with a circuit, and then we're going to simplify the circuit, and then we're going to simplify the circuit again. And as we go out this way, we keep on reducing the number of resistances. And now we're like halfway done with the problem. We're way out here. And then once we get way out here, we start calculating voltages and currents and start working our way back. So it's like a boomerang problem, yes? So let's get started here. So this is our original circuit, and what we have to do is we have to look for resistances that are either pure series or pure parallel. I like to call them ivory pure, because ivory is pure something. I don't know what it is, but it is pure. And when I say pure, if you have a circuit that has pure series, well, you'll have like two resistances, and you should be able to circle the two resistances, and there's only one pathway. And notice, with the circle, there's only two spots. One wire here where a wire goes into the circle, and one here where the wire comes out. So those two would be pure series, yes? If I had another right here, if I circle these two, notice the circle I made, there's only one wire going in. Hello, one wire. There's only one wire coming out. And how are those two wired in between? That's pure what? Remember, with a series circuit, if you undo one light bulb, the other one goes out. You see how the other one would go out in series? Yes? In a parallel circuit, if you undid one light bulb, what would the other one do? It would stay on. It would actually brighten.
Oh, that's
Or remain the same.
Another circuit.
What's that?
Like that's another circuit. Like
It's
it's gonna be added to.
going to be added. These wires go on to another part of the circuit. This is just part of the circuit.
Oh,
Okay? So that's parallel right there, yes. Okay? Now, let me just show you this and then we'll take a little break. Those two might look at first like they're in pure series, yes? However, if you really look closely, to be pure, you can only have one wire going into the circuit and one wire coming out. And really, it appears like there's that, like, yes? But what's the problem? Oh, we have another little thing over there. So those two are not ivory pure. That's not ivory pure series. Okay? So we're going to be identifying the pure series and the pure parallel. Take a break, come on back, keep it going. Okay, welcome back. How's everyone still feeling?
Totally awesome. How are you feeling?
Totally awesome. Couldn't feel better. So we were looking at this combination circuit here where the current goes through one light bulb, then splits. Some goes this way, some goes that way. Reunite it to complete the circuit. Yes? If you rewrite the circuit in a more textbook fashion, it could look something like this. Okay? Also, folks, sometimes it's even drawn this way, which is even a little tougher to recognize. It could be drawn like this. So that circuit right there is equivalent, is identical to this circuit right here. Those are one and the same. And what we're going to do is we're going to find the current in each resistance and the voltage across each resistance. And we use the boomerang technique where we're going to keep reducing the resistances. So we need to identify a pure series part or a pure parallel. And usually there's one or the other. And it's not just like your choice. Like it's either going to have a little piece in there that's pure series, or it's going to have a little piece in there that's pure parallel. So it's like a little skill to identify the pure part of the circuit. Does anyone recognize where there's some purity? Yes, Samantha.
Pure parallel,
Yeah, which two?
the box area.
Yeah, these two up here, that's pure parallel, yes? So what we're going to do is we're going to replace that circuit by drawing an equivalent circuit and reducing those two down. So I draw another circuit. And these two here are going to be replaced with that one right there. So it's these two right here that are going to be simplified down, yes? And if I want to find one resistance that's equivalent to those two in parallel, what formula do I need to use? Bradley?
1 over the total resistance is 1 over the resistance.
That's what I'm talking about. So what we're going to use is the formula 1 over RT equals 1 over R1 plus 1 over R2. So 1 over RT is going to equal 1 over 8 ohms plus 1 over 4 ohms. And I like to use my x to the negative 1 button. So I would hit 8 x to the negative 1 plus 4 x to the negative 1 equals, and then hit my negative 1 button. I know my R2 is going to come out smaller than 8 and smaller than 4 because the equivalent resistance is always smaller than any of the individual resistances in parallel. Anyone have that crunched out? Bradley.
2.7 ohms.
2.7 ohms? Anyone double check that? Awesome. Okay. So I come back over here. And I replace this here with 2.7 ohms. And basically, what is this first one? 2 ohms, yes? So this was 2 ohms. This was 4 ohms. And that was 8 ohms. This was a 12-volt battery. This is a 12-volt battery. So now I keep going. And what sort of purity do we have now, Ariane? Yeah, these two are in pure series. So if I take a look at these two right here, that's ivory pure series. Okay, so I'm going to redraw the circuit once again.
you make it 1 though?
We're going to keep simplifying the circuit until we get down to one resistance.
So you just use the one over and
Okay?
You just want.
You want one. Sometimes you might even be asked, hey, with this original circuit over here, what's the equivalent resistance of this whole circuit over here? What's the equivalent resistance? And you have to keep simplifying it. And what is this total resistance here going to be right here? Well, how are the two resistances, how are they wired right there? Series. So we know we have to go RT equals R1 plus R2. So RT is going to equal 2 ohms plus 2.7 ohms. So RT is going to equal 4.7 ohms. So this is 4.7 ohms. So the total resistance of the whole circuit is 4.7 ohms. Or you could say the equivalent resistance of the whole circuit is 4.7 ohms. And remember we were doing the boomerang technique, yes? Well, we're halfway done. We went out to here, and now we just got to bring it on back. When you simplify it down, to just one resistance, you know you're like halfway done with the problem. You went all the way out. And now that we have the total voltage and the total resistance, what else can we calculate with that last problem down there? Let's go over here, Hannah. The current, yes? So basically I could calculate the current over here, and I could say, well, V total equals I total times R total. The total voltage is 12 volts. The total current is what I'm solving for. And now I know the total resistance of the whole circuit is 4.7 ohms. So if I solve that for the total current, what do I end up getting? 12 divided by 4.7. 2.6 units, Jessica? 2.6 amps. Once you know that the total current leaving the battery at this circuit is 2.6 amps, you know the total current leaving this circuit right here is 2.6 amps. And you know the total current leaving over here is 2.6 amps. Because all three circuits are equivalent. Now here's the important part. Pay attention here, people. We did the boomerang thing. We started here. We went, whoa, out further, but now we're going to be making our way back, yes? And when we make our way back, and we start coming back from here back to there, then we have to take a close look. What are we going back to? Well, when we go from here back to there, we're going back from this thing, and we're going back to these two in series. So basically, look, we're going back to a pure series. And when you go back to a pure series, the thing you carry back with you is the current. Because in a series circuit, the current is the same. So if we know the current going through this resistance right here, is 2.6 amps, when we come back over here, we know the current going through this one is 2.6 amps, and the current going through this one is 2.6 amps. So when you go back to an Ivory Pure series, you carry back or bring back the current. When going back to Pure series, bring back the current. Now that we brought back the current, bless you, now that we brought back the current, what can we calculate for each of those, Risa?
The voltage.
Excellent, because anytime you have 2 out of the 3, you can get the third. And Risa recognized, oh look, right here. We have the current and the resistance, so we can get the voltage for that guy. And over here, we have the current and the resistance, so we can get the voltage. Excellent job, Risa. That's exactly what we have to do. So now we do a little Ohm's law calculation. V equals I times R, and V is going to equal 2.6 amperes times 2.7 ohms. A little help, Bradley? 2.6 times 2.7?
7.0.
We'll just say 7.0 then. 7.0 volts. So we know the voltage across this one, 7.0 volts. And then for the other one, V equals IR. 2.6 amps times R, 2.0 ohms. I don't like how I wrote that there. I'm going to take that out of there. And what about this one? It's going to be what, 5.2?
Yes.
So we know that this one here is 5.2 volts. You guys with me? We're coming home now. Boomerang's almost back. So now we're going back to the first circuit. Now, do you see this guy right here? Right there. Yes? Watch. That guy right there? That's the same as this one right here. Since this one is the same as this one, these values right here, we could just bring them all back, yes? So we know that, this right here is using 5.2 volts and has a current going through there of 2.6 amps. But what about this piece here? This guy here, when we go back, back over to there, what are we going back to? Ivory Pure parallel. And what's the same, what's always equal in a parallel circuit? Do you remember, Diana? In a parallel circuit. Don't get paranoid. Volts. So basically, when we go back this way over here, we know that the resistance of this was 2.7, the voltage across this was 7.0, and the current through here was 2.6 amps, what are we going to carry back and give to each of these guys over here? The voltage. So we know over here the voltage was 7.0 volts. So we know over here the voltage across this one is going to be 7.0 volts. And the voltage across this one is going to be 7.0 volts. You got it, Samantha. But first, let's make a little note of that. Right here. When going back to pure parallel, bring back the blank. Fill in that blank. Let's go to Cindy. When going back to pure parallel, bring back the voltage. And then Samantha said it perfectly. Hey, look right here. We have the volts and the resistance. And right here, we have the volts and the resistance. So what can we calculate for each of those? The current. And then we solve the whole darn thing. We solve for the current in each resistance, and we solve for the voltage across each resistance. I'm running out of room here, so let's see, I guess. So we have 7 volts equals I times 8 ohms. Little help there. 0.88 amps. So the current in that top one is 0.8. And what about the current in the bottom one? What do we got? 4/7, which is no. Oh, 7/4, 1.8. Okay. Sorry everything's so small and sloppy, but there you have it, ladies and gentlemen. Do you see like what I mean by like the boomerang effect? First we went out here, then we went down there, and then we start bringing values back, and we start bringing values back. Samantha?
So just like when you brought the bolt back, you only did that from like, cause just to get exactly pure series what, so
The volt?
feel like you got the.
No, the volt, when we brought that 7 volts back, what are we going back to? Pure parallel.
So where'd you get the 5
This guy over here? This guy is just identical, the same as this guy. So I just brought the values back. It's the same resistance. See, this guy here is the 2 ohm. This guy is the 2 ohm.
So could you calculate the voltage there?
Why you have
See, look, we have all the answers for this guy right here. We have all the answers.
Is that like given?
We know we just calculated it.
5.2 we have.
Yeah, we calculated. Where did we calculate the 5.2?
Oh, okay, I see.
Over here. Right there. Okay. Here's one for you guys to try. So we want to do the boomerang technique.